Hi, everybody, and welcome back to MTED 110. Today we're going to be starting Chapter 6, and Chapter 6 is all about fractions. Sorry. I'm really excited about this chapter, and in particular, Chapter 7, because we get to play with a lot of manipulatives virtually. And this is the chapter that is going to change your opinion about fractions, I hope. I'm really, really hoping because I don't know about you, but when I was younger, I really, really hated fractions. Sometimes I still hate fractions now. Um, but I hope that you will leave this chapter with a better understanding of fractions because you shouldn't be afraid of them. I know they can induce a lot of anxiety, but remember, you have power over the numbers, not the other way around. And if you don't feel that way, it's because there's something about them that you're missing, an understanding that you're missing. And hopefully, these lectures and our meetings will help you gain that understanding. Let me go ahead and pull up the slides. Okay, so chapter 6 is all about meanings for fractions. So first we're just going to talk about what fractions are. And then chapter 7 is about operating on fractions, or operating with fractions, I should say. So let's start here. First, we need some acknowledgement. So this is one of those moments where you have to take a moment and think about this. So which is greater, 3 or 11? Okay, now let me ask you this. Which is greater, 3/5 or 17/30? All right, so here's the question I have. When you read the numbers 3 and 11, did you see the quantities or just the numerals? And then in contrast, when you read 3/5 and 17/30, did you see those quantities or did you just see the numerals? So the idea here is that you have an emotional response to 3 and 11, and you have an emotional response to 3/5 and 17/30. And what you should feel is about the same, frankly. But if this one was much more difficult or much more frightening, that's what we're here to address today and in these lectures and beyond. Or how about this? Think about this. Which one of these numbers is the greatest? What do you think? What do you think? Well, after you play around a little bit, you'll realize that those are all the same number. This is the same number. 3/5, 18/30, those are the same number. Zero point 0.6, that's the same number. 60%, that's the same number. So this is just four different ways of writing the exact same number. And that's the key. So again, this is why we spend so much time on chapter 2, because when you see these things, you should be seeing numbers, not numerals, right? So whenever you see something like this, you should be able to get a visual idea of where it is on the number line, about how big it is. Same thing with something like that. You should be able to kind of guess where it is on the number line and about how big it is. Is it bigger than 1? Is it smaller than 1? How far away from 1 is it? Is it closer to a half? Is it closer to 1? We're going to talk about all that stuff in these lectures here. And then 0.6, same thing. That's just a decimal representation, and this is just a percent representation. 60% is zero point 0.6. Okay, so let's start with this. First, we want to understand the meaning of this symbol. So we're specifically talking about what that symbol A over B means. What does it mean? Well, this is the part whole meaning of that symbol. And basically what it tells us is that the denominator gives us how many equal sized pieces the whole or the unit is cut up into. So for example, if I write something like, 14/27. Well, the denominator down here is telling us how many pieces the unit is cut up into, the whole. So if you had one object and you cut it up into 27 pieces, that's what that denominator is telling you. And then the numerator is telling us how many of those pieces we're going to take. So I had 14 over 27. The denominator says, hey, take that unit and cut it up into 27 pieces. And then after you've done that, the numerator says, take 14 of those pieces. And that's the quantity that we're talking about. We're talking about 14 of those 27ths if you were to take a unit and cut it up into 27 pieces. All right? So this is where, the whole like the pizza example and all that kind of stuff, that's all going to play very well in here. So here's the idea. The quantity A over B, is formed by taking A parts of size 1 over B. So in other words, A over B is 1 over B, A times. That's what it means. So A over B is 1 over B, A times. Just like before, 14 over 27 is 14 times 1 over 27. So if you took 1/27th and added it 14 times, you would have 14/27ths. That's the idea. So that's a critical understanding that you have to carry away, you have to carry with you from now on. And this is what your students need to understand too. All right, so let's have another thinking moment here. In these drawings below, in which of the drawings are the parts of equal size? So this drawing has some parts, this one has some parts, this one has some parts, this one has some parts. The question is, in which of those are the parts of equal size, and then what size are the parts? So just take a minute and think about that. All right, now that you've thought about it, talk out loud about talk out loud about what you said. I mean, what you were thinking. Just take a few minutes to talk about it out loud. Okay, now let's discuss it here. Um, what is the which of the following are the parts of equal size? It turns out that in all the first three, the parts are all equal sized. Yeah, that's the thing. Notice in the first one over here, this is a rectangle, right? And there's a dividing line, a halving line. So the rectangle is cut into two equal sized halves. But then each of those halves is also cut in half. So it's cut in half over here, and it's cut in half over here. So each one of these parts represents 1/4 of the whole. There we go. So that's 4/4 to make up a whole. Get it? 4/4, that's one, right? It's one whole. That's the idea. And the key thing to recognize here is that it's not about the shape. So notice the word that I used here. I said equal size, not equal shape. They don't need to be the same shape, but they do need to be the same size. That's the important part. In the second one, those are also the same size. It may not look like it at first, but they are indeed the same size. You can kind of see it if you think about the geometry a little bit. If you cut this in half, right? And if you were to focus on, oh, I don't know, maybe just this one right here. Oops, maybe this one right here, and then this one down here, right? Two of those make up the same space as this triangle right here. So that's why those are all the same size. In fact, maybe I shouldn't have highlighted that one. I should have highlighted this one. There we go. Imagine taking these two triangles and essentially rotating them. So like, take this one and rotate it and take this one and rotate it. And what you're going to get is you're going to get a triangle that looks like that. And that's exactly what's over here. So even though they're not the same shape, they are the same size, and it's a quarter once more. Okay, what about the next one? The third example, yeah, those are all the same size. Similarly, we've cut the rectangle in half, and then we cut each of those halves in half. So each one of those is a quarter. Oh yeah, these are a quarter also. 1/4, 1/4, 1/4, 1/4. All right, and now what about the last one? No, the last one, they are not equal sized, and I think you can see that pretty clearly, right? This piece right here is definitely not the same size as that piece, and that's easy to tell visually. And this is going to be an important distinction to keep in mind because if those pieces aren't the same size, then we can't make sense of the fractions that we're talking about. And that's going to have wide-ranging implications because those pieces being equal size is essentially why we need common denominators. So when we get to the next chapter, chapter 7, we'll talk about common denominators and stuff. Actually, you know what? No, we talk about it in this chapter. Yeah, we talk about it in this chapter, but maybe the next lecture. Can't remember. Anyway, so we need those pieces to be the same size because remember, what is this? A over B is A times 1 over B. So when we're making sense of a fraction like this, we need the pieces to be the same size because really all we're doing is we're counting. We're counting how many of them we have. And it doesn't make sense if they're different sizes, right? You wouldn't say like 1, 2, 3, like those things aren't the same, right? You need the things to be the same to actually count them, right? Okay. Or to count if you're using them to represent fractions, I should say. Okay, so now think about this one too. Take a moment and just think about what quantity is represented in each of these three pictures. So take a minute and think about it. All right, now that you've thought about it, take a minute and talk out loud. Say out loud what you were thinking in your head. Say it to the wall, say it to the room, to the ghost, to behind you, to your group members preferably, but just talk out loud and say a little bit about what you were thinking. Okay, now let's talk about it together. So you might have noticed something. For one, you can add, you can see that in the second example here, that quantity represented is 3/4. That's the idea. It's 3/4. And the reason for that is because each one of these is a fourth. And actually, this is really just another example of something like this, right? It's the same thing right there. So if three of those pieces, those equal size pieces are shaded, that's telling us that we have 3/4 of the whole. That's the idea, of the whole. What's the unit? So that's 3/4. Over here, this one you can see is 1/2. Notice that it doesn't matter the shape, right? The shape does not matter. What matters is the size. And then what about number one? Number one, you might be tempted to say 1/4, but then once you look at it for a minute, you're like, wait a minute, wait, what? That, I can't tell because is this a fourth? Is that a fourth? Like, you can't really tell, right? The reason you can't tell is because the pieces are not equal sized. They're not equal sized. And actually, you can tell right away that this piece right here is definitely smaller than this piece right here in terms of size. So they're not equally, I'm sorry, the pieces are not equal sized. And because of that, we can't meaningfully use it to talk about fractions. So that's the idea. The sizes need to be, or sorry, the pieces need to be equal sized. That's what you're going for. Okay, this is another definition. This is the sharing equally or partitive division model of or interpretation of a fraction. So a fraction AB can interpret it as meaning this. A wholes are partitioned into B parts. So imagine you had A objects and you partitioned it into B parts, each part being an equal share. That's the idea. And we actually saw this back in chapter 3. I'm pretty sure it was lecture 3B, in fact, where we were talking about, or we watched those videos of students doing the equal sharing, right? Thomas, that was his name. Thomas was showing us how to use this understanding of division. And because he understood that so well, he's going to transfer very nicely to fractions because he understands division. Fractions are basically division, right? So there's that structure, that scaffolding, that foundational knowledge coming back over and over and over again. Okay, and then this is my favorite interpretation. We've talked about this before. We talked about it back in 3B, I think, actually. Um, this fraction A over B can interpreted to mean repeated subtraction, or in other words, the big important question, how many B's fit inside of A? How many B's fit inside of A? And this is called, this is sometimes called the measurement interpretation. And that's the reason that I like this interpretation so much. I explain it right here, but the truth is that we measure things using ratios. We measure things by dividing them into ratios of units that we already understand. So an example that I usually like to give is this. Imagine that I'm holding a gigantic ball, okay? And I say that that ball has a volume of 900 cubic centimeters. Let's say volume equals 900 cubic centimeters, right? What do I really mean when I say its volume is 900 cubic centimeters? Think about it for a minute. What do I mean when I say that, really? Well, let's think about it like this. If I'm saying the volume is 900 cubic centimeters, what I'm saying is that if I had a bunch of cubic centimeters, I could fit 900 of them inside that ball. But then did you hear it right there? Did you hear the language? I said if I had a cubic centimeter, I could fit 900 of them inside that ball. So in other words, I can fit 900 cubic centimeters inside this thing. So each cubic centimeter is 1/900th of the volume. That's the idea, right? So we measure things by ratios. That's a ratio right there. And that's how we measure things. How many of these little things fit inside of this other thing? That's how we measure, right? So division and fractions are extraordinarily important just for understanding how to measure things even. Um, Oh, there you go. Why do you find a common denominator when adding fractions? Well, because our cubic centimeters are units, we can just count how many of them fit, right? You can just count how many that, and if you end up with 900 of them, you'll get the whole ball. So I'll put it this way, each cubic centimeter, 1 cubic centimeter equals 1/900th of our volume, right? 1/900th of the volume. And so if you keep adding 900 of those, then you're going to end up with 900 cubic centimeters equals 900 over 900 of our volume. Or in other words, that's the volume. The volume is 900 cubic centimeters, right? Because 900, that cancels out. There you go. So that's the idea. That's the idea. um, all right, so this is an important definition too, and you do need to know this well because you're going to have to refer to these things a lot. So a fraction, if you have a fraction that looks like this, 1 over n, it is called a unit fraction. And it's called a unit fraction because 1 is the unit. 1 is the unit. So just keep that in mind. If it's 1 over a number, that's a unit fraction. All right, so now let's talk a little bit about parts and wholes. And then I think we're going to jump right into the manipulative in a second here. So let me ask you this. If the 4 flowers below, if this represents 2/5, what does the whole look like? Think about it for a minute. Okay, now that you've thought about it for a minute, try to write down what the whole would look like. Draw the whole now. All right, now let's do this one together. So if the 4 flowers below are representing 2/5, the thing to keep in mind is that we're relating this picture to the quantity 2/5. So if this is 2/5, then my question is, what is 1/5? Let me write that here. What is 1/5? So if this, excuse me, if this is 2/5, what's 1/5? Well, 1/5 is just going to be 2 of those flowers, because if I have 2/5, there they are. There's the 2/5. So each one of these is representing a fifth. Now, if we have to figure out what the whole is going to be 5/5. So we need 5 of those to get a whole. So I'm just going to use, I'm going to use stars here. There we go. There's another fifth. There's another fifth. And there's another fifth, right? 1/5, 1/5, 1/5. So that's the whole. This is what the unit looks like. So the unit is this. There we go. That's how we figured it out. So we were able to look at parts and extrapolate what the whole was going to be because the parts were equal size, right? So that's kind of how this works. All right, so here's what we're going to do now. We're going to play with a manipulative. And this manipulative is called, they're called pattern blocks. Let me go ahead and switch to the camera so I can show you what the physical one looks like. So you might have seen these. They're all over elementary classrooms. You might have some in your own home right now. I know I've got some because I've got kids. But we use these things to help students understand numbers in general, but they're pretty handy for fractions too. So first you have this. You have a yellow hexagon, right? And it's just a thin little chip. It's like a plastic chip, right? So you've got a hexagon. You've got yellow hexagon. You've got a red trapezoid. You've got a blue rhombus, a rhombus here, or kind of like a parallelogram, right? And you've got a green triangle, So these are the 4 pieces: yellow hexagon, yellow hexagon, red trapezoid, blue rhombus, and then a green triangle. So those are the pieces. There are some other funkier pieces. We'll talk about those in a little bit too. We'll see them, I think we'll see them in chapter 7. But anyway, the idea is this. We want to use these to help students understand fractions. And here's how we're going to do it. Let me go back to the slides here. This is actually a good time to mention a pedagogical choice. This website I found is a little bit better for pattern blocks. And we're going to compare 2 websites right now. But let me pull it up and I'll tell you what I mean here. Let's look at the toy theater virtual manipulative first. There we go. Okay, so this is toy theater, and they have a pattern blocks emulator here, so you can use this. And it's pretty straightforward. You just drag the pattern blocks onto the board like so. This is one of those other pattern blocks. We won't use it too much. Um, this is a good time to compare virtual emulators here. So this one I found interesting because if you drag these things, there's a certain physics going on. And if you touch the other blocks, it'll kind of like touch them and you can like roll them around each other, right? So I encourage you to play with this. You could actually pull this up right now. Just follow that link on the slides, and it'll be right here. Or, I'm sorry, this is Toy Theater, so you should have that link already, Toy Theater, or just toytheater.com, and then go to the pattern blocks manipulative. But this one is all right, and it's kind of cute, but the thing that bugs me the most is that we can't put the pieces on top of each other. Yeah, so what we want to be able to do is we want to be able to put the pieces on top of each other. Yeah, I'll clear the canvas for right now. So that's why I don't really like this particular virtual manipulative. But this other website, Cool Math for Kids, looks like this, and theirs you can actually put them on top of each other. So I kind of like this one a bit more. Here we go. I'll do this. Like, there's that. You can also turn the blocks like so, but you can put them on top of each other, and that's critical because what we're going to do is we're going to compare sizes of things, and so we want to be able to put things on top of each other. So here you might be able to see that, oh, that trapezoid is like one half of the hexagon, right? That's the whole idea. Is it one half? Sure it is, because if I have two of them, then it covers the whole. Boop, there it is. So two halves makes a whole. Pretty cool, huh? So I actually recommend using this virtual emulator, and this is the one that I mentioned on your activity as well. So your activity is going to be very similar to what we're going to do right now. So first, let me delete some things here. You can just hit this little trash or hit start over. There we go, start over, clear. All right, so let's go back to the slides for just a second here. And it says, okay, if the green triangle is 1/3, right? So if the green triangle is 1/3, then how much is the unit? What's the unit? So let's go back and check. All right, so if this is 1/3 here, let me drag a triangle here. If that's 1/3, what does the whole look like? Okay, well, let's see, 1/3. If that's 1/3, then 3/3 would be the whole. So if I drag three of these down here, this one I'm going to rotate. You can probably guess where I'm going with this. There we go. That's what the whole looks like, the unit. Or in other words, it's a trapezoid. There we go. Actually, I think there are some better. No, no, okay. Trapezoid. There it is. So if this thing is representing 1/3, if this is 1/3, then this must be 1. And that's exactly how we help students understand what fractions are. Okay, okay, so the next one said, if the yellow hexagon is the unit, so if the hexagon is the unit, what's 1/3? So let's take a look at that. Let's go back to here. Let's start over. And we're saying if this is the unit, so if that's the whole, what is 1/3? What's 1/3 of this shape? Well, I'll spare you the suspense. It's going to be the rhombus. It's the rhombus because you can see here that if you take two of these rhombi, these rhombuses, I don't know if rhombi is the correct pronunciation, don't quote me on that, then three of these things fits. Oops. Three of these things fit inside the hole, just like that. So this is a way for us to compare thirds and wholes, and we saw thirds and wholes for the trapezoid as well. But there's an interesting thing going on here, and the interesting thing is that you get to pick the unit. So the unit changes depending on what you're looking at and what you're selecting. And this is what's so interesting about this. You'll hear me say it a lot, and especially in chapters 8 and 9, I believe, or chapter 7. I think it's chapters 8 and 9. You're going to hear me say the phrase of what a lot, of what, of what, of what. So a third of what? A third of what? So before we said that this triangle represented a third, and we found out that it was a third of this. So this triangle is 1/3 of the trapezoid. The trapezoid is our referent unit. Referent unit. We'll talk about that more later. Okay, what was the next question on here? If the blue rhombus is 1/6, then what is 1? Let's go check. Okay, so let's clear this. Click start over. if the blue rhombus is 1/6, then what is the unit? What's 1? Well, remember we saw that 3 of these made up a hexagon, so I'm just going to cut to the chase. This is 3 rhombuses. Remember this one was like here, and you had another one up here, or something like that. So this is 3 rhombuses. That means this would be 6 rhombuses. So this rhombus represents 1/6 of this whole figure, both of these. So in this case, the unit is actually these 2 hexagons. These 2 hexagons are representing 1. They're representing the whole, and that's the idea here. Okay, then what is the next question here? The next question says, if the red trapezoid is the whole, what fraction is the blue rhombus of the whole? Let's go see. Okay, let's start over again. We'll click start over, clear the board, and then it said if the red trapezoid is the whole, then what fraction of that whole is this blue rhombus? Well, if we lay it over top, you can probably see. It's going to end up being 2/3. But why is it 2/3? Are you sure it's 2/3? I mean, sure, it kind of looks like it's 2/3, but how can we visually guarantee that it's 2/3? Well, again, if this is the whole, then we should be able to show the 2/3, and here they are. There's 1/3, and here's 2/3. Remember, we just saw a moment ago that these represent thirds, and there's 2 of them. And if I had a third one, then lo and behold, I've got the whole, right? There you go. Lo and behold, I've got the whole. There's a nice pun for you. Okay, what's the last bit here? Okay, so the last bit says use pattern blocks to model 5/6. And to do that, what you have to do is you first have to decide what you're going to let represent the whole. So in this case, what I'll do is I think I'll pick the hexagon. Let's go back. Okay, so I'm going to pick the hexagon to represent the unit. And now I need to model the quantity 5/6. So the way I'm going to do that is I'm going to find out what 1/6 of the hexagon is, and it's this trapezoid, or say this triangle. This is 1/6 because 6 of these fit inside of this hexagon. So I'm just going to go ahead and put 6 of them here. What? That's weird. Hold on one second. Refresh this here. There we go. Let's put that right there. It goes here. Oh, I forgot you can also like double click. That's right. Double click them and they'll pop up. There's 3, or just click once, I should say. I double clicked and I got an extra one. Okay, there's 4. And just turning this around. There's 5. So there are 5/6. So this is how we would represent 5/6 for the children. And you would even write, you can go down to drawing tools here, and you can write 5. Hey, where'd you go? Come back here. Maybe I should, I changed the shape color. Hold on a second. Thought I'd be able to write 5/6. That's strange. That's the protractor. Maybe. That's strange. See, there you go. This is a good reason to check these manipulatives, right? Or to check these websites, because I thought I would be able to write that. I know you can select things. For some reason, it's keeping me on the select function and not the other function. Let's see if the help helps at all. Okay, there's that circle shape, patterns. Can make interesting patterns here. Protractor. Open the drawing menu. So maybe that's what's going on. Open the drawing menu. Oh, you know what? Maybe. Nope, not letting me. Interesting. So try this on yours and see if you can do that. For some reason, it's not letting me draw on here. To be honest, this is actually not the manipulative that I use. I actually use an app for my iPad, but I had to pay like $4 for it. Let me pull that up really quick so you can see what it looks like. Okay. Where did you go? Pattern blocks. There it is. So it's right, you can't really see it here, but it's right here. And it's kind of cut off because I have this formatted specifically for my slides, so I don't want to mess it up too much. But it's the same kind of thing here. You can drag and drop these things and so on. And there's a little pen item down here, so you can write. Actually, that's 2/3. Where's my eraser? There's an eraser part of it. Come back to this. This is going to be 2/3. There you go. So this app is just called Pattern Blocks. If you want to purchase it, you can, I suppose. It's like $4, I think. And this company has a few different apps. And actually, I'm gonna use the Pattern Blocks app on here too. Maybe next time I'll set up a different scene so that you can see the full screen. Anyway, we can still use these two virtual manipulatives, and that'll work just fine. Okay. Let's go back to the slides. All right, so the next one was representing 2 1/3. So let's do that, and then I'll leave the others. Actually, no, we'll do 5/12. In fact, let's do this. Let's do 5/12. 2 and 1/3, I think you could do that one pretty easily. Let's go over here and pull up that website again. There we go. So let's model 5/12. That's what we're trying to model. Okay, so if I want to model 5/12, I need a shape that I can cut up into 12 equal sized pieces, and then I need to take 5 of those pieces. Well, you'll notice that all of these pattern blocks, they're not really divisible by 12 that nicely, but we can say that our unit is 2 of these. So our unit is this, 2 of those, and I can cut that into 12 pieces. So if I want 5/12, I just need to put 5/12 on here. 1, 2, 3. Okay. Hey, hey, come back here. Hey, there we go. All right, there's that 4, and then one more. There we go, something like that. 5/12. There it is, 5/12. So this is how you would model the quantity 5/12 for a child. And you'll be surprised, it makes a lot more sense to them when they can see the pictures, right? Because what does 5/12 mean? Like, oh man, that's just a symbol, right? I need some actual intuition before it makes sense to me. Okay, let's go back to the slides, and I think that's about it. Yeah, that's it. Let's play. Oh wait, I didn't go back to the slides yet. Come back. There we go. Oh, maybe I forgot to show this. I can't remember if I transitioned or not. So maybe I was just talking over my slides the whole time. This is. Let me repeat this. This is 5/12. So the two hexagons here, the two yellow hexagons, those are representing the whole in this case. And then over here, I've got 5 of those triangles. And so because I chose the two hexagons to represent the whole, these 5 triangles represent 5/12 of the whole. Okay, sorry about that, my bad. Okay, so now let's play. Let's take a look at activity 6A. Activity 6A is almost identical to what we just did a moment ago. So let me pull it up here. Activity 6A. Okay, so here it is. So it tells you to go to this website, and you're just going to do pretty much what I did right now. You're just going to model these things, and you're going to paste your models on this document here. So you do need to use this website, and you do need to try to get things on here. You can paste it, and then you can write on here, something like that. If you're having trouble with that, just let me know, and I can see what I can do to help. Same kind of thing. We saw this before. The questions are the same ones as before, but slightly varied. If the blue rhombus is 1/6, what is 1? If the red trapezoid is the whole, what fraction is the blue rhombus? And so on and so on. And then using pattern blocks to model these numbers. There's also this question, which is similar to one we saw in the lecture. And that's it. That's it for that activity. Okay, so like I said, this one's a little bit short. The next lecture is going to be a little bit long because we have the rest of this chapter to cover in the next lecture. So let me see here. Yeah, I guess that's it. Yep, that's it. All right, then I'm going to sign off here, and I will see you all in the next lecture, and I'll see you in the collaboration meetings. Have a good one.